Hey kiddos, today we're going to talk about Note 7.3 limits. We're going to look at them a little bit further graphically and numerically. So really what's happening to a table of data and look for patterns. So today we really want to understand the concept of a limit, and we want to use the definition of a limit to estimate limits numerically and graphically. All right, so we're going to take a very popular problem in math called the maximum area of a rectangle. And we're going to find the dimensions of a rectangle with perimeter 24 inches that yields the maximum area. So when we think of what this rectangle could look like, I have a rectangle and I know that I have my length and I have my width. So I really have to think about what I know. So when I think about rectangles, the two things I do really have formulas for, I have formulas for area and I have formulas for perimeter. So I know that if I want to find the perimeter, I can take twice the width and twice the length, and that equals 24. I also know that the area is going to equal the length times the width. So I am going to rewrite the area function. I really want to find the area in terms of W or in terms of L. I have too many variables going on right now. I have 3 variables, it's kind of a problem, and I want to maximize the area. So this is the equation that I'm going to have to work with in the end. So what I'm going to do, I'm going to come over here to my perimeter equation and I'm going to solve it for L. So first thing I'm going to do is get rid of some of these 2's. So this is going to become W plus L equals 12. So I can divide a 2 out of each side. And in the end, L equals 12 minus W. So if I want to write area as a function of width, that means the only variable I can have in my problem is W's. I know that the length is 12 minus W. And I can take this W here. If I rework this, I have area as a function of width equals 12W minus W squared. So I can take and put that equation into a calculator and I can fill in the table. So let's go ahead and get your graphing calculator out and let's look at some things. First of all, if I do a quick sketch of the graph, I think actually I'm going to graph this on the other page, but if I do a quick sketch of the graph, my graph looks something like this. It's a concave down parabola. I know because of this statement right here, I have an x-intercept at 12, and I also have an x-intercept at 0, which thinking logically means my halfway point is 6. So I know that this maximum value happens when x is 6. Like I can look at my parabola, I can tell that for sure, but let's look at it in terms of limits. So go ahead and turn your calculator on and go to y equals and type in the equation. It'll be x, 12x minus x squared. Once you have that equation typed in, I want you to go to your table set. So second, I can't remember what button it is. It's second window, and you can go to your table setup, and I want you to start at 5, and I want you to count by 0.1. So instead of counting by ones like we normally do, let's count by 0.1s, and then I want you to go to your table. And I want you to hit pause, and I just want you to take a minute to fill in the values on this table. Or you can just copy them as I write them. All right, so this one's going to be 35, and I pulled these values straight from the table. This one is 35.25. And here we have 35.99. And here we have 36. And as I go the other direction, I'm just basically rewriting these because we all know that a parabola is symmetric. So the numbers to the left of the vertex and to the right match up. Okay, so when I think about what is happening, as I start here and come in from the left and go towards 6, I am approaching an area of 36. And when I come in here and I come from the right and I look at those numbers on my table, they are getting closer and closer to 36. So I know that when I look at my graph that this number here is going to be 36. So if I think about, and I'm just going to regraph what I had on the other page, this is area as a function of W, and this is W. There's my parabola, and here's 6, and here's 36. So if I think of what's happening, I can say that the limit of the area in terms of W as W approaches 6 is 36. So that's going to be your algebraic equation based on the data that we have in our table. And if I want to talk about what does this mean in English this would translate to as W approaches 6 from both directions, and it is important that you say from both directions, the area in terms of W, so A of W, approaches 36. So my W is approaching 6 and my A of W is approaching 36. So you see that word that we have been talking about every day in class. If we see the word limit, we have to just automatically tie that with the word approaches. In this case, it actually is my maximum area, and it is 36, but I can definitely see that my graph is continuous, and when I look at my graph, that when I come in from the left and when I come in from the right, I am approaching that Y value of 36. All right, so when we think about limits graphically, we kind of have 3 cases, and this is where it seems easy until it's not easy and it gets confusing. So the first graph, I'm just going to graph some kind of like cubic looking polynomial function. Your graphs don't have to be perfect by any means. I'm just trying to give you some different looking graphs. Let's make C right here. So, or that's L. Okay, so we have this cubic looking polynomial function, and we have this case where f of c equals L. So like this point is actually on my graph. This function is continuous, and we've talked about this in class. So if we think about this, the limit of my function as x approaches c equals L. So verbally, if I think about what I'm really saying, is that as x approaches c from both directions, f of x approaches L. And remember, if the function is continuous, U-O-U-S, at c, then the limit always exists. So in this case, I drew a polynomial function, so my limit is always going to exist because it is continuous across the entire domain. All right, so let's draw case 2. Let's draw a parabola, but let's put a big old hole in our parabola. So right here at C and right here at L. So this is a case where f of c does not equal L. So we talked about removable discontinuities in class the other day. So this is a case where we had a removable discontinuity. We had a factor that we were able to cancel the numerator and the denominator, the numerator with the denominator, and reduce that to 1. So the thing about this, though, is if we think about the limit and we think about the word approaches, as x approaches c from both the left and the right, the y value of this function is approaching L. So even though I have a point that does not exist at C, I can approach it from both directions and the limit still exists. So then what if I have a graph that looks like this? So what if I have a horizontal line with an open circle, and then somewhere else I have a closed circle? So I'm going to say the open circle and closed circle both have an x value of C. I'm going to give this line value a value of L, and I'm going to give my solid point a y value of P. So in this case, f of C does not exist at L. So at L, there's an open circle, the limit does not exist. However, at f of C, I do have a point that exists that is point P. This is the one that really gets a lot of students because the limit of this function as x approaches C, because of the word approaches, as I come in here from the right and I come in here from the left, this graph is approaching a y value of L. So even though the existing value is actually P, it is approaching a value of L. All right, so all right, a couple problems that we just need to think about in our head. As f of x approaches a different number from the right side of C than it approaches from the left side of C. So if we think of a problem, and this is one that you are going to start seeing, but it's going to be a new function. It was in your notes earlier this week. But the limit as x approaches 1 of the absolute value of x minus 1 over x minus 1. And we know that when we reduce these are going to reduce to 1, except for the fact that the numerator is always positive, but there's a chance the denominator could be negative. So the denominator could be negative or positive. So what happens on this graph is, in this case, at C, which in this case is 1, but I'm just going to put C equals 1 for this particular graph, you're going to have right here at 1, you're going to have an open circle that goes this way to represent all the positive values for this. And right here, you're going to have an open circle at -1, and we're going to go, that's an open circle, and we're going to go this way with another horizontal line. So anytime you have the absolute value of a function over the same function, your graph will look something like this. At whatever value makes your denominator 0. So like when we come over here, and we take x minus 1 equals 0, x really equals 1. So that's why this jump happens at 1. When you see a graph that looks like this, the limit does not exist. Okay, so the limit does not exist because as I approach the C, which in this case is 1, as I approach 1 coming in from the left, I approach a y value of -1, and as I come in from the right, I approach a y value of +1, so my overall limit does not exist. Make sure you know this function. Okay, we can talk about it in class if you're still confused about that. All right, and then f of x increases or decreases without bound as x approaches C. So basically, this is talking about graphs with vertical asymptotes. So vertical asymptotes, better known in the future as a vertical asymptote, VA. So in this particular case, if we have a vertical asymptote at C, and this is going to be a rational function, so this is something that makes your denominator 0, and it's not a removable discontinuity. If we think about the limit of this function as x approaches C, when you come in from the right, you are increasing without bound. But when you come in from the left, you are decreasing without bound. So because we're basically going opposite directions and we are not approaching the same value, this is another limit that does not exist. So anytime we have a vertical asymptote and we're looking for the limit at the vertical asymptote, the limit does not exist. Now, hypothetically, if there was some other point, I don't know what we want to call it, a over here, the limit at a does exist because on that one little section of the graph is continuous. Okay, so the limit doesn't exist at the vertical asymptote, but it potentially exists many other places on the function. All right, and then the last random case, f of x oscillates between two fixed values. So this is a graph we didn't talk about. You'll see why here in a second, but the limit as x approaches 0, and if you want to put this in the calculator just for fun, you can. This graph kind of looks like this, and then it just like goes crazy, and then it like levels out or whatever. This is a horrible version of this graph, okay? But the limit on this graph also does not exist as x approaches 0. So as we get closer and closer, oh, I should have scooted this graph over. I'm going to erase it. Don't erase yours, but put it in the calculator and see what it looks like. It looks like this, and then here it just like literally goes nuts, and then it looks like this. So as x approaches 0, they say the limit of this graph does not exist as well. So okay, hopefully this reiterated some things about limits. Hopefully it cleared a few other things up. If you have questions on any of this, we will talk about them in class tomorrow. We'll probably also have to talk a little bit about tables in your calculator and adjusting the values, but we can do that when you get to class. So have a wonderful evening, and I will see you tomorrow.